Let me ask you something. Why do we call it the speed of light? Think about that. Of all the names we could have given the most fundamental speed limit in the universe, we named it after something you can see with your eyes. As if light invented that speed, as if photons own it. They don't. The speed of light has almost nothing to do with light. And that naming accident, that historical quirk, has confused more people about more physics than perhaps any other single phrase in the English language. My name is Leonard Susskind. I've been a theoretical physicist at Stanford for over 50 years, and I spent a good chunk of that time thinking about the structure of space-time, about relativity, about the geometry of the universe at its most fundamental level. And I can tell you, the constant we call c, 299,792,458 meters per second, exactly by definition since 1983, is not a property of light. It's a property of space-time itself. It's the speed at which causality propagates. It's the conversion factor between space and time. It's the cosmic speed limit, and it would exist in the universe with no light at all. Let me show you why, and I'm going to be precise about this. Start with a question that sounds simple. What is light? When James Clerk Maxwell published his theory of electromagnetism in 1865, he did something extraordinary. He took the known laws of electricity and magnetism, Coulomb's law, Ampere's law, Faraday's law, combined them into a unified set of equations, and discovered that those equations predicted waves, oscillating electric and magnetic fields, leapfrogging through space, each one generating the other. And when he calculated the speed of those waves from the known constants of electricity and magnetism, the permittivity and permeability of free space, the number he got was very close to the measured speed of light, about 3 times 10 to the 8th meters per second. Maxwell's conclusion was immediate and correct. Light is an electromagnetic wave, and from that moment on, the speed of electromagnetic waves became known as the speed of light. A perfectly reasonable name in 1865. But it was a name that carried a hidden assumption, that this speed was a property of electromagnetism, a feature of Maxwell's equations, something specific to electric and magnetic fields. And here's the thing. That assumption is wrong. Let me be very precise about this. The speed c does not come from Maxwell's equations. Maxwell's equations inherit c from space-time. The arrow of explanation points the other direction from what most people think. Light doesn't go at c because of some special property of electromagnetic fields. Light goes at c because c is the speed at which any massless thing must travel, and photons happen to be massless. If electromagnetism didn't exist, if you deleted it entirely from the laws of physics, the speed c would still be there, sitting in the structure of the universe unchanged. How do we know this? Because c shows up in places that have absolutely nothing to do with light. Take gravity. In 1915, 50 years after Maxwell, Einstein published his general theory of relativity. And one of the first things people calculated from Einstein's field equations was the speed of gravitational waves, ripples in the fabric of space-time itself. The answer? c. Exactly c. Not approximately c, not close to the speed of light, the same constant, 299,792,458 meters per second, derived from a completely different area of physics. Gravity has nothing to do with electric charges or magnetic fields. Gravitational waves are not electromagnetic waves. They're distortions of space-time geometry propagating outward, and yet they travel at exactly the same speed. In 2017, the LIGO and Virgo collaborations detected gravitational waves from a neutron-star merger, event GW170817, and about 1.7 seconds later, the Fermi satellite detected a gamma-ray burst from the same source. The source was roughly 130 million light-years away. When you work out the numbers, the gravitational waves and the light traveled the same distance, about 1.2 times 10 to the 24th meters, and arrived within 1.7 seconds of each other. That constrains the difference between the speed of gravity and the speed of light to be less than about 3 parts in 10 to the 15th. 3 parts in a quadrillion. They're the same speed. Not because gravity copies electromagnetism, but because they both obey the same spacetime. Now here's where it gets interesting. Let's go deeper. The speed c shows up in nuclear physics. Einstein's famous equation, E equals mc squared, published in 1905 as a consequence of special relativity, tells you that mass and energy are related by a factor of c squared. That equation governs nuclear reactions, radioactive decay, particle-antiparticle annihilation. When the uranium-235 nucleus undergoes fission in a nuclear reactor, the mass difference between the original nucleus and the fragments is about 0.1% of the total mass. Multiply that tiny mass difference by c squared, and you get about 200 million electron volts, or roughly 3.2 times 10 to the minus 11 joules per fission event. That's the energy that powers nuclear reactors and, regrettably, nuclear weapons. And c in that equation has nothing to do with light. It's a conversion factor between mass and energy built into the structure of the universe. The speed c shows up in particle physics. Every massless particle, not just photons, but gluons, the carriers of the strong force inside atomic nuclei, must travel at exactly c. Neutrinos, which are not massless, but have extraordinarily tiny masses, less than about 0.1 electron volt per c squared, compared to the electron's mass of 511,000 electron volts per c squared, travel so close to c that for decades physicists assumed they were massless. In 2011, there was even a brief sensation when the OPERA experiment at Gran Sasso reported neutrinos arriving 60 nanoseconds earlier than light would over a distance of 730 kilometers from CERN. The implication would have been that neutrinos travel faster than c. Spoiler, it was a loose fiber optic cable. The universe's speed limit held. And here's the really strange part. The speed c even shows up in quantum mechanics in a context that has nothing to do with anything moving at all. The fine structure constant, alpha, is a dimensionless number about 1 over 137 that characterizes the strength of the electromagnetic force. Its value is the elementary charge squared divided by 4 pi times the permittivity of free space times Planck's reduced constant times c. There's c again, embedded in a fundamental constant that governs how atoms behave, how chemistry works, why the periodic table looks the way it does. Delete light from the universe, and alpha would still have a value determined partly by c. So why is c what it is? Why 299,792,458 and not some other number? Here's where I need to take you into the geometry of space-time. And this is where Einstein's real genius lies. Not E equals mc squared, that's a consequence. The real insight was this: space and time are not separate things. They're woven into a single four-dimensional fabric, and the relationship between space and time is described by a geometry that Hermann Minkowski formalized in 1908. In ordinary Euclidean geometry, the geometry you learned in school, the distance between 2 points follows the Pythagorean theorem. Distance squared equals delta x squared plus delta y squared plus delta z squared. Every direction is the same, every axis is equivalent. Minkowski showed that spacetime has a different geometry. The distance between two events in spacetime, what physicists call the spacetime interval, is not delta x squared plus delta t squared, it's delta x squared minus c squared times delta t squared. That minus sign changes everything. It means time is not just another dimension like space, it has a different character, and c is the conversion factor that lets you compare spatial distances to temporal durations. It tells you how many meters of space are equivalent to 1 second of time. The answer is about 300 million meters. 1 second of time corresponds to 300 million meters of space. And that ratio is c. Think about that for a second. The speed of light is not really a speed, it's a ratio. It's the exchange rate between space and time, baked into the geometry of the universe. It would exist in a universe with no particles at all, no photons, no electrons, no quarks, just empty space-time, and c would still be there because it's a property of the stage, not the actors. Now you might ask, and you'd be right to ask, if c is really about geometry, why does it show up as a speed limit? Why can't anything go faster? This is the beautiful part, and it requires a little bit of careful thinking. In Minkowski geometry, the minus sign in the space-time interval creates a structure called a light cone. At every event in space-time, every point specified by a location and a time, you can draw a cone that represents all the directions you could travel at speed c. Anything inside the cone is reachable. You can get there from here. Anything outside the cone is unreachable, not just difficult to reach, not just beyond our current technology, unreachable in the same way that you can't draw a triangle with angles that add up to 200 degrees in flat Euclidean geometry. It's not forbidden by a law of physics sitting on top of space-time, it's forbidden by the structure of space-time itself. This is not an engineering problem, this is a geometry problem. When you try to accelerate an object with mass towards c, its relativistic momentum increases without bound. At 90% of c, the Lorentz factor gamma is about 2.3. At 99%, gamma is about 7.1. At 99.99%, gamma is about 70.7. To reach c exactly, gamma goes to infinity. You'd need infinite energy to accelerate even a single electron to c. The energy of a particle moving at speed v is gamma times mc squared, and as v approaches c, gamma diverges. No finite amount of energy will get you there. People sometimes ask me, what if we discover something that breaks the speed limit? What if tachyons exist? Tachyons are hypothetical particles that would always travel faster than c. They show up in some equations as mathematical possibilities. Beautiful idea, doesn't work. If tachyons existed, you could construct causal paradoxes, situations where an effect precedes its cause, and the logical structure of the universe breaks down. Every known consistent quantum field theory excludes tachyons from the physical spectrum. They're a mathematical artifact, not a prediction. And in string theory, which I've spent decades working on, tachyons in the spectrum signal an instability. They mean you're expanding around the wrong vacuum, not that faster than light travel is possible. But it gets worse. Even the word speed in speed of light is misleading. When we say c is the speed limit, we're implying something is moving, covering distance over time. But in general relativity, Einstein's theory of gravity, space-time itself can expand, and it does. Right now, the most distant galaxies we can observe are receding from us at speeds well above c. Galaxies beyond about 14.5 billion light-years are moving away from us faster than light right now as I'm talking to you. This is not science fiction. This is observed, established cosmology, measured by the redshift of distant supernovae, first demonstrated clearly by Saul Perlmutter, Brian Schmidt, and Adam Rees's teams in 1998, work that earned the 2011 Nobel Prize. Does that violate relativity? No, because nothing is moving through space-time faster than c. The space itself is stretching. The galaxies aren't flying apart through space. The space between them is growing, and general relativity has no speed limit on the expansion of space. The speed limit applies to objects moving through space-time, not to the evolution of space-time itself. If this distinction sounds subtle, it is, but it's precise and it matters. Here's another place where the name misleads. People hear speed of light and they think of light as special, privileged, the fastest thing, the unique thing that defines the limit. But light is not unique. It's just the most familiar massless particle. Gravitons, if they exist as particles, and the quantum theory of gravity is famously unfinished, so let me be careful here, would also travel at exactly c. Gluons travel at c inside the color force field of protons and neutrons. Any massless particle whatsoever, regardless of what force it carries, regardless of what interaction it participates in, must travel at c. The speed limit is democratic. It doesn't belong to light. Light just got there first in our understanding, and so it got its name on the building. Let me tell you why this matters beyond just naming conventions. The confusion between speed of light and cosmic speed limit leads to real conceptual errors. I've seen smart people, physicists even, talk about what would happen if the speed of light were different. They imagine a universe where light goes at half its current speed, and they try to work out the consequences. But this is confused thinking. If you change c, you're not changing a property of light. You're changing the geometry of space-time. You're changing the ratio of space to time. You're changing E equals mc squared. You're changing nuclear physics, atomic physics, chemistry, biology. You're changing everything. It's not like turning down the brightness. It's like rebuilding the universe from scratch with a different fabric. In natural units, the units that theoretical physicists actually use in their calculations, we set c equal to 1. Not because it's convenient, though it is, because it reflects the truth. Space and time are the same thing, measured in different units due to a historical accident. The meter was defined based on the circumference of the Earth. The second was defined based on the rotation of the Earth. These are arbitrary human choices. In the universe's own units, if such a thing made sense, c would be 1. 1 unit of space per 1 unit of time. The fact that we measure it as 300 million is a statement about our measuring sticks and our clocks, not about the universe. Could I be wrong about any of this? Let me think about what it would mean for me to be wrong. The claim that c is a property of space-time rather than a property of light is not a speculative idea. It follows directly from special relativity, which has been tested with extraordinary precision. Time dilation has been measured in particle accelerators, in GPS satellites. The GPS system has to correct for both special and general relativistic effects. Without those corrections, your position would drift by about 10 kilometers per day. And in direct observations of muon decay. Muons created by cosmic rays in the upper atmosphere have a half-life of about 2.2 microseconds. They're created at altitudes of about 15 kilometers. Even at nearly the speed of light, they should only travel about 660 meters before half of them decay. But we detect them on the ground. Why? Because time dilation stretches their lifetime in our reference frame. The measurements agree with special relativity to extraordinary precision. Could there be modifications at extreme scales? Perhaps. Certain quantum gravity proposals, loop quantum gravity, some string theory scenarios, suggest that spacetime might have a discrete structure at the Planck length, about 1.6 times 10 to the minus 35 meters. If so, there might be tiny energy-dependent corrections to the speed of massless particles. Some researchers have searched for this by looking at gamma rays from distant sources, gamma ray bursts billions of light years away, to see if higher energy photons arrive at slightly different times than lower energy ones. So far, the results from the Fermi Gamma Ray Space Telescope, analyzing bursts like GRB 090510 at a distance of about 7.3 billion light years, show no detectable energy-dependent delay. The Lorentz invariance that gives us C holds the scales at or even beyond the Planck energy. But I'm a theoretical physicist, and I know that nature might have surprises. The important point is that even if there are tiny corrections, they would modify C at the 20th decimal place or beyond. The core insight that C is geometric, not electromagnetic, would remain intact. When I first understood this as a young man, when it really sank in that the speed of light isn't about light, it changed how I think about everything. It's the kind of realization that makes you see the whole structure of physics differently. You start to see C everywhere. In the relationship between electric and magnetic fields, they're the same field seen from different reference frames connected by C. In the relationship between energy and momentum, E squared equals P squared C squared plus M squared C to the fourth. In the relationship between mass and the curvature of spacetime, everywhere you look, there's this one number, this one ratio, stitching the universe together. And it was named after the wrong thing. Some people find it pedantic to insist on this distinction. After all, everyone knows what you mean when you say the speed of light. And that's true. In practice, it doesn't matter. But in understanding, in really grasping what the universe is telling us, it matters enormously. Because the lesson is this: the speed c is not a fact about one particular phenomenon. It's a fact about the arena in which all phenomena take place. It's not a property of the actors, it's a property of the stage, and the stage came first. The geometry of spacetime exists prior to any particle, any force, any field. The particles are ripples in that spacetime. Light is one such ripple, a beautiful, visible, familiar ripple, but just one of many. After 50 years of working with these ideas, I've learned something about physics that I think is worth passing on. The universe is not built out of things. It's built out of structure, out of relationships, out of geometry. The particles we observe, the forces we measure, the light we see, these are all manifestations of something deeper, something more abstract, something that our brains, evolved as they were to navigate the African savanna, were never designed to picture. We do our best. We use analogies, we use mathematics, we use thought experiments, and sometimes, if we're patient and honest, we catch a glimpse of what's really going on. The speed of light has nothing to do with light. It has everything to do with the nature of reality. And I find that, after all these years, not diminishing, but beautiful. The universe has a structure, and that structure is elegant. And we are allowed, privileged really, to spend our brief time here trying to understand it. That's what makes physics, for me, endlessly exciting. After all these centuries, the universe can still surprise us with the simplest things. Thank you for listening.